Hi everybody, I hope everybody is doing well. In this video lecture, we'll talk about some examples about inner products and also some additional results which I haven't been able to highlight during the lecture notes or is best expressed through a video lecture rather than written notes. Okay, so let us start. But before starting, this material is based on lecture notes of March 26, 31st and April 2, 7, 9, 14 and 16. So the correct order is to look at the notes first and then to watch the video. Oh, okay, so let us start. So the first remark that I want to make is about using the Cauchy-Schwarz inequality. So let's remember the inequality first. So this simply says the absolute value or the modulus in the complex case of the inner product of two vectors v and w is less than or equal to the product of their norms. And this works in any inner product space or Hermitian inner product space. Now, equality happens if and only if one is a multiple of the other, or V and W are linearly dependent. Okay, fine. We prove this in the notes. What I want to talk about here is its usage. So you can use this inequality even in some cases where there is no inner product space around. So you just want to prove an inequality and you just make up your space yourself. Okay, so there are many nice examples of this. Let me do a basic one just for demonstration. So prove that following inequality holds. Okay, you have a sum inside absolute value a1 times cosine theta 1 plus a2 times cosine theta. This goes up to an times cosine theta n. Show that this is less than or equal to square root, and this is a longer square root, n times sum of squares of the ai's. Here, ai and theta I are just assumed to be real numbers. And when does equality occur? Okay, so simply stated, this is some inequality about real numbers. There's no vector space around or there's no inner product, but we can make it up. So let's V to be Rn with its usual inner product, standard inner product. Okay. And let us set up two vectors. So one is simply a1 up to an, and w is cosine theta 1 up to cosine theta n. Now, apply Cauchy-Schwarz inequality for these two vectors. I will abbreviate with CS. Okay, now their inner product this is the standard inner product, so it's just a1 cosine theta 1 plus up to an cosine theta n. What about their norms? So norm of v is simply a1 squared plus up to an squared to the 1/2. No question about that. So how about the norm of w? This time you have cosine square theta 1 plus up to cosine square theta n to the 1/2. And we just use the simple fact that cosine square is bounded above by 1. And this gives us immediately, this is less than or equal to square root n. Okay? And when you combine them all, the Cauchy-Schwarz inequality immediately gives this desired inequality. So, I mean, we're done. And what about the equality case? If you want equality, first of all, you must have equality in this last step. And that means all these cosine squares must be 1. Let's write that down. For equality, first of all, cosine square theta I equals 1 for each I. So this implies cosine theta I must be plus or minus 1. But that's not all. I mean, the other condition is V must be dependent with W. V and W should be dependent. So A1, AN must be proportional to cosine theta 1, cosine theta n, this vector. And depending on the signs of each component, plus or minus, you have the same structure in AIs. First of all, the absolute values of all AIs must be equal because these are all plus or minus 1. Furthermore, their signs should also be compatible. I mean, let me not write that down, but it's kind of clear how to finish it from. Okay, this was just an example of the usage of Cauchy-Schwarz to prove an inequality. And this is kind of a nice subject, and you can produce very interesting examples. Actually, there are whole books dedicated to using Cauchy-Schwarz in interesting ways. Okay, let's not go too much deeper into that. Okay, now one topic which I sort of skipped in the notes is Bessel's inequality. It's kind of an important theorem, actually. So the setup is you have V together with an inner product. It could be just real or Hermitian. Or Hermitian inner product space. Okay. And suppose you have an orthogonal set in this vector space. Remember, this means the inner product of any two distinct VI's, so VI inner product Vj for I not equal to j is 0. I don't assume that it is a basis, so it could be, but it doesn't have to be. Okay, well, the linear independence of the sets is kind of, we know that if you don't have zero vector here. Okay, fine. In this quite general setup, we have the following thing. For any vector in V, we have the inequality norm of V square is greater than or equal to following sum. Okay, you take inner products of V with VKs, square them up, and divide by the norms of VKs. Okay. Now, if this set is orthonormal, that would mean that the lengths of these VKs are 1, then you wouldn't see this denominator. You can also see Bessel's inequality in that form, which is equivalent. Okay, now before proving this, the proof will not be very hard, but maybe I should make a remark first. Already if n is equal to 1, this is already interesting. So for n equals 1, what do you get? So modulus V squared, you just have one term in the sum, which is VV1 squared over V1 squared. So if you unwind this, it just tells you VV1 is less than or equal to norm V squared, norm V times norm V1. This is just Cauchy-Schwarz. So Bessel's inequality generalizes Cauchy-Schwarz inequality. Okay. Now how to prove it? Well, we just have to refer to our orthogonal projection formula. Okay. So orthogonal projection to where? So let's W be simply the span of these orthogonal vectors, span of V1 up to Vn. Okay, now compute the orthogonal projection of V to W. We know how to do that from the notes, and the upshot is we have a clean formula for it. Okay, you just have to compute the inner products of V with these vectors and suitably normalize, then multiply by the relevant vectors. That was the procedure. You do this for each of them. This is the projection. And the schematic way to remember this is, well, in this big space you have the subspace W. This is your vector V, potentially outside W. What you want to do is to find this unique vector here so that, okay, this is exactly proj WV. The unique vector such that V minus proj WV is orthogonal to W. Right, and by analyzing that, we arrived at this formula. Now, one basic fact is that, again, this was written in the notes, this projection has norm less than the norm of the initial vector v. Now we could square both sides without changing anything here. And let's write down what this says and we'll get the answer. So this norm square of this thing, well, you can take inner product with itself. So this will, sorry, this is v, momentarily be somewhat lengthy. So this whole thing inner product with itself okay, this whole thing is less than or equal to modulus v squared. But okay, if you compute this, what do you get? Well, of course, you have the inner product of a term with the same term over the right-hand side. That will give you something. And there are cross terms. But the cross terms will give 0 because the VI's are orthogonal. So VI inner product VJ will be 0. So cross terms will be 0. And you'll just get the inner product of each term with itself on the right side. And that exactly gives you a sum. Let's find out what it is. Well, you have, first of all, the same inner product twice. That will give me this thing. It's not 1, it's I, sorry, and I runs from 1 to n. Then you have VI to the power 4 here, but then you also have VI, which will give you VI squared. Okay. And if you cancel the square with 2 of the factors down here, this is exactly Bessel's inequality, what you want. Okay, so a question that I want to leave to you to investigate when equality happens. So when does equality happen in Bessel's inequality? Okay, let me leave that part to you. Okay, now let's do something else. We have a nice procedure for producing orthogonal bases for an inner product space, namely the Gram-Schmidt algorithm. Let's apply this to some particular setting. So, a small subtitle is Gram-Schmidt and orthogonal polynomials. So the topic of orthogonal polynomials is a huge subject which deserves its own courses and books and everything. So this will just be some kind of beginning example which tells you that something nice is going on here. Okay, so let's consider V equals PNR specifically. So this is real coefficient polynomials of degree less than or equal to n. So this is a finite dimensional vector space, as we all know. It's n plus 1 dimensional. And we can put various inner products on the space. That's the whole point. We can put many different inner products on V. Well, one of them we know very well is the integral inner product. So inner product of f and g is the integral from a to b f of x times g of x times dx. Here I need a to be less than b for this to make sense. Okay. Now, a point that I want to make is in this integral, you have some flexibility here. I mean, there's room to add something. I mean, we're integrating the product, but we could also take some kind of weighted integral. I mean, instead of integrating with respect to dx, we could use another measure. So we can generalize this. By putting a weight function. Okay, so here's how it will go. So suppose that wx is a function which is non-negative on AB, and for ease of presentation, let me say it is allowed to be 0 only at finitely many points. This is definitely not the most general thing you can write, but let's stick to this. Okay, then I'll change the integral inner product slightly. So it's again going to be an integral, but this time of f times g times this weight function. Okay, so the first exercise for you, which is rather standard at this point, show that this is really an inner product. Okay. So this is quite routine. I mean, you'll just have to check all the rules one by one. Okay, now let's choose a special W and try to apply Gram-Schmidt. This kind of thing comes up in applications more often than you would think. I mean, so this is something that you see many times. Okay, so here's a simple example of this weighted inner product. So take V to be P2R, so degree less than or equal to 2 polynomials, and for simplicity, let's take A and B to be 1. So F times G times, let me make the weight function x squared. Okay, so this weight function x squared is non-negative because x squared is non-negative, and it is 0 only at 0. It's non-zero everywhere else, so it fits my definition. Okay, now the question is, find an orthogonal basis for V. Okay. Now, since the inner product depends on the weight function, the notion of orthogonality also depends on the weight. So this will not be the same answer as if you didn't have this x squared here. I mean, it will be a different answer from the standard inner product. Now we'll apply the Gram-Schmidt process. Okay, you could look up the relevant lecture while watching this maybe. Start from any basis. Okay, why not take the standard one, 1, x, and x squared to start with. Okay, and also let's give these names v1, v2, and v3. All right. Now, how does this Gram-Schmidt procedure go? Well, here's the algorithm. So W1 is simply V1. I don't change anything. So it is 1. Now for W2, you take V2 and you try to sort of chop away its projection to the previous W's. So V2 W1 divide by W1 W1 W1. That's what I should write. But then this requires a bit of computation. So you need to find out these two inner products. Well, let's find it. So V2 W1. We just apply the definition and nothing else. So this is going to be integral from -1 up to 1. Now, what is V2? V2 is x. You just substitute everything. W1 is 1. Don't forget the weight function, which is x squared. So you're integrating x cubed dx from -1 up to 1. But this is an odd function and this is a symmetric interval, so by some chance here we got 0. Okay. Well, this relieves the computation a little bit. This means this is 0 and you could take W2 equals V2. It's kind of specific to this example, as we realize. If the situation was a little bit different, we would get something else. Okay, let's move on. Now, for W3, the idea is the same. So you start from V3 and you try to get rid of all of its components with respect to the previous vectors that you obtained. So you should subtract V3 W1 over W1 W1 W1, and also take away V3 W2 over W2 W2 W2. That's what we should compute. So again, we need to look at these inner products. Let's find them. So V3 W1. This should be the integral from -1 to 1. Okay, now read everything. So V3 is x squared. W1 is 1. The weight function is x squared. So this time we're integrating x to the power 4. And this time it's not 0. It is x to the 5 over 5 evaluated from -1 to 1, which is 2 over 5. Okay, so this is not going to be 0. W1 should also be computed. It's -1 up to 1. 1 times x squared dx. So this gives x cubed over 3 -1 to 1. And this gives 2 over 3. So we got the two numbers here. Now, we should also compute the other two, this V3 W2 and W2 W2. but I think this is going to give you 0, so let's check that. So V3W2 is again the integral from -1 upon 1 of, okay, x squared. Now, what was, what was W2? W2 is x, okay. And the weight function, okay, let's count. So x to the 2, 3, 5. X to the power 5 is an odd function, so its integral on the symmetric interval will give you 0. That's good. So this term is not here. Okay, so we conclude by looking at this. W3 is V3, which is x squared minus 2 over 5 divided by 2 over 3, and W1 is 1, and the next one is 0, so I'm not writing that, so it is simply x squared minus 3 over 5. And the answer to this question is, now we got everything, 1x and x squared minus 3 over 5 is an orthogonal basis. Okay. And the final thing I want to do in this lecture is to give an example of the method of least squares. So there was already one example in the notes, which was about fitting the best line to some set of points. Now let's try to fit the best parabola to another set of points. So the question is, find the equation of the parabola that best fits to the points okay, I'll list some points. Minus 3, 8, minus 2, 3, minus 1, 0, 0, 1, 1, 3, 2, 6, and 3, 15. Okay, now that best fits in the sense of method of least squares. So the precise meaning is, so minimize the differences of norm of the difference with respect to the standard inner product. Okay, we'll come to that. But maybe also it's worthwhile to draw a picture. So this is x, y. You are given some data points. So minus 1, 2, 3. I mean, minus 3, 8 is maybe somewhere here. Minus 2, 3. Minus 1, 0. 0, 1. And here we have 1, 3, 2, 6. Maybe somewhere here. And this point 3, 15 should be somewhere high. Maybe somewhere around here. Well, you want to fit a parabola to all of them. But in a moment, we'll see that there is no single parabola that fits all of these 7 points at once. That's too many points. So instead, you want to find the best choice in the sense to minimize an error, right? So that's the point. Okay, so how do we do that? Now, well, the most general parabola equation will look like y equals ax squared plus bx plus c. And we want to find a, b, and c ideally, right? We want to find A, B, and C. Okay, we have 7 conditions. 7 points give 7 conditions. And although this equation is kind of nonlinear equation, when you plug in x and y, the conditions will become linear. So for example, if you plug in the point minus 3, 8, so I mean, just passing through minus 3, 8 means 9a minus 3b plus c equals 8. You want that. And you do this for each of these 7 points. Let me not write the points here, but you get 7 equations. So the next one is 4a minus 2b plus c equals 3. The next one is a minus b plus, please check this yourself as well. Okay, this is 0. If you plug in 0, 1, you get c equals 1. Then a plus b plus c is 3. 4a plus 2b plus c is 6. And 9a plus 3b plus c equals 15. So you have 7 equations and 3 unknowns. This is obviously too much to ask for. So, I mean, you have too many conditions. To hope for an exact solution. And it's not hard to show that this system has no solutions. They just start from somewhere like c equals 1, then play with these other equations, and what you will get will cause a contradiction in some of the other equations. Let me not do that, but that's quite simple. Okay, what do we want to do then? So instead, we think of this like a matrix equation, and it would look like this. Okay, you have 9, 4, 1, 0, 1, 4, 9 here. Then minus 3, minus 2, minus 1, 0, 1, 2, 3 here. And all ones here. So it's a 7 by 3 matrix. Your unknowns are A, B, C. And your right hand side is 8, 3, 0, 1, 3, 6, 15. Now the whole point is, if you say that these column vectors are, can I order them in a funny way, like v1, v2, v3 in the reverse order for some reason, then their span will be the column space of this matrix, of course. But the point is, this other vector v does not belong to the column space, so there is no solution. And the whole idea is, okay, replace v by something else so that there is a solution, but do this in the cheapest way without causing too much error. And the method of least squares says replace v by the orthogonal projection of v to w and solve the new system. Okay, let's do that. That's quite algorithmic at this point. Well, to be able to compute the orthogonal projection, maybe it's best to find an orthogonal basis for W first. Okay, so our starting basis is V1, V2, V3, which is these three columns. Let me write them once again. Okay, 1, 1, 1, 1, 1, 1. There should be 7 of them. And V2 is minus 3, minus 2, minus 1, 0, 1, 2, 3. And finally, V3 is 9, 4, 1, 0, 1, 4, 9. Now we should do Gram-Schmidt. Now, first of all, W1 is V1. You don't have to change anything. Now, for W2, you should chop off this V2 W1 over W1 W1 W1. But fortunately, V2 W1 is 0 with respect to the standard inner product. You have minus 3, minus 2, minus 1, but then you also have the plus counterparts here. They cancel. So this term is 0, and you just get V2. This is the reason I ordered them like this. It's quite easy to see what Gram-Schmidt is doing in this order. Otherwise, you could do it otherwise, but the computations will be a little bit different. That's all. Okay, finally, W3. This time I start from V3. I chop off V3 W1, W1 W1, W1, and also V3 W2, W2 W2, W2. Now one needs to compute these. Okay, this is V3 minus. You can compute these two numbers easily. Let me just write the answers. Please check my computation. The top one gives you 28. The bottom one gives you 7. W1. Now for V3 W2, again, this fortunately gives 0. You have 9, 4, 1 and minus 3, 2, minus 2, minus 1 here. But you have the positive ones 1, 4, 9 and 1, 2, 3 here, which cancel the negative ones. So this second thing is 0. So the final answer for W3 turns out to be the vector. Again, please check. 5, 0, minus 3, minus 4, minus 3, 0, 5. Okay. Okay, now having computed an orthogonal basis, the next thing to do is to compute projection. The projection of V along the subspace W is simply VW1 over W1, 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 then VW2, W2, 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 and the same for VW3. Okay, there's a bunch of computations which I will not reproduce here, but I'll write the results that I found so you could cross-check. So this is 36 over 7W1 plus 15 over 14 W2 and 17 over 14 W3. Again, please check. Okay. Now, what you have to do next is to rewrite the system with the right-hand side V replaced by proj VW. Now rewrite the linear system with V replaced by proj WV. Okay. Let me write the answer again and please check. So the first two numbers don't change. They are again 8 and 3. But the others do change. I mean A minus B plus C. Now in the original system, let me check my notes, it was supposed to be 0. Now it is not. It is instead something like 3/7. And C, which was supposed to be 1, is now not 1, it is 2/7. And likewise the others change. So A plus B plus C is 18/7. In the original system, I mean the old value was 3, so it's close to 18/7 but different. So 4A plus 2B plus C is 51/7. In the original system again, this number used to be 6. 51/7 is greater than 6. It's close, but not really. Okay, 9A plus 3B plus C is 101/7. Again, the original value was 15. That would make 105, but it's 101. It's quite close, but not exactly the same. So you have a new system, which is kind of approximating the old system, and you should solve this. This is easy to solve. Solution you can immediately find using some basic arithmetic. It is 17/14. B is 15/14, and C is 2/7. And this gives you the answer. I mean, the best parabola that fits is apparently this parabola. Okay, that's our answer. It would be a nice exercise to use a computer to plot the points and also plot this parabola and see if it really looks good enough, just close to them. I didn't do it, but it's a nice exercise. Okay, so that finishes this problem. When you are looking up method of least squares from other sources, you could also see some other formula using A transpose A and so forth. That's also kind of, that will lead to the same answer. That doesn't use Gram-Schmidt. It's shorter there, but you have to invert a matrix, so it's longer there. It's not computationally much cheaper than what we did. It's more or less equivalent. I prefer this way because it's more conceptual using projections. The other way kind of obscures how you should think about it. Okay, so that's all for today's lecture. Thank you very much.